All right, this is Chapter 4, Test Review, Worksheet number 2. This is the first page. Non-calculator, so we have to be able to work these problems without a calculator. As we are looking at indefinite and definite integrals, uh, we want to be able to identify which method to apply to find the solution. And whenever you see polynomials, when you see in terms of x, first thing you want to try is can you uh, uh, simply use power rule to find your solution? That's the first thing you want to test. You don't want to resort to u-substitution as your first option. So look to see if you can expand by eliminating parentheses. Look to see if you can get your variable in the numerator, and then also rewrite every term as rational exponents. Okay, if you can separate then you want to use power rule. So here we can simply expand because we only have one term in the denominator. We can split this up into the sum of individual fractions. And we'll rewrite square root of x as x to the 1/2. So we have these three fractions. Now we want to bring these denominators up to the top. Remember, anytime you are dividing like bases, you're going to be subtracting exponents. So 2 minus 1/2 is 3/2. 1 minus 1/2 is 1/2. And then this x, we want to bring this up to the top. We don't want this x in the denominator, so simply changes to x to the negative 1/2. So now we have each term separated by plus or minus, no parentheses, all the variables in the numerator, and everything represented as rational exponents. Okay, so we can now apply power rule for integrals, where we're going to be adding 1 to the initial exponent. So 3/2 plus 1, or 3/2 plus 2 over 2 is 5/2, divided by that new exponent, and we go down the line. 1/2 plus 1 is 3/2 divided by 3/2. Negative 1/2 plus 1 is positive 1/2 divided by 1/2, plus c. Hey, remember, anytime we're finding indefinite integrals, we have to include a plus c to represent the family of functions that share the same derivative. Okay. Now to resolve these complex fractions, we're going to bring all these fractions up to the top by taking the reciprocal, flipping it. So 5/2 becomes 2/5, 3/2 becomes 2/3, and then 1/2 becomes 2. And you could write your answer as rational exponents or as radicals, but I just left my solution as rational exponents. Okay, number 2, let's see if we can resort to simply using power rule. But the problem is that even after we rewrite the original problem using rational exponents, we can't distribute the 2x through. Order of operations tells us that we have to take care of exponents before we can deal with multiplication. So we have to now look to another method, and u-substitution is going to be next in our list. So to identify the u value, we want to first look at what's inside the parentheses. We're going to let that be our first guess. So our u value, we're going to let it be 1 minus 3x squared. Find the derivative with respect to x, so du over dx. 1 turns into 0. Negative 3x squared becomes negative 6x. Solve for dx, we cross multiply. Solve for dx. Dx is du over negative 6x. So now we want to look back at our original problem and make our substitution. So we want to substitute everything that we can in terms of u. So this parentheses, what's inside the parentheses gets replaced with u. The 2x does not go away at first. So 2x times u to the 1/2. Dx gets replaced with du over negative 6x. So now we look to see what we can cancel out. So the x's cancel out. So this tells us that we can continue with this method. Okay. This negative 6, we want to pull this in front as a coefficient. So negative 1/6 times 2. So the negative 2 over 6 are reduced to be negative 1/3. So negative 1/3 times the integral of u to the 1/2. So we go through power rule. 1/2 plus 1 is 3/2 divided by 3/2. Flip the reciprocal. So negative 1/3 times 2/3 becomes negative 2/9 u to 3/2 plus c. But remember, you want to represent your solution in terms of the original variable that you started with. So replace u back in terms of x, 1 minus 3x squared to 3/2 plus c. All right, let's look at number 3. Again, we want to check to see, can we resort to simply using power rule, okay, by expanding numerator, having the variable and rational exponents. In this case, this parentheses is only raised to the first power, so we can distribute the 5 root x through. So I'm going to rewrite as 5x to the 1/2. We're going to distribute through, and when we distribute through, we get 20x to the 1/2 minus 15x to the 5/2 because we're adding exponents. 1/2 plus 2 is 2.5 or 5/2. So now, no need for u-substitution. We have every term separated by plus or minus, all of our variables in the numerator, rational exponents. Okay, we go through power rule. 1/2 becomes 3/2 divided by 3/2. 5/2 becomes 7/2 divided by 7/2. Bring the denominators up. Multiply through, and don't forget the plus c. Okay, number 4, anytime you see a trig, a function involving a trig, a problem involving trig function, anytime you see in the parentheses that is anything more than the x, you have to go through u-substitution. So in this case, we want the u value to be 3x squared. And if we look ahead, we know that 3x squared, the derivative will turn into 6x, which will cancel out with the remaining x here. Okay, you always want your derivative of your u value to end up canceling out any remaining x's. So our u value is 3x squared. Derivative 6x. Solve for dx. dx equals du over 6x. We make our substitution. Secant squared. 3x squared is replaced with u, and dx is replaced with du over 6x. We see the x's cancel out, but the coefficients do not, so we have to keep that as in front. So 5/6 times integral of secant squared of u. We know we do have a rule for secant squared of u, which is tangent. And if we know the derivative rule for tangent being secant squared, then it should make sense that secant squared becomes tangent. So 5/6 tangent of u plus c, and then finally replace our u back in terms of x. All right, number 5, integral of x squared times square root of 7 minus x. Let's see if we can resort to simply using power rule, and we can't. We have more than one term in the square root, so we're going to have to go through u-substitution. Okay? We can rewrite this problem as the integral of x squared times 7 minus x to the 1/2 dx. So our u value, our first guess, will be what's inside the parentheses, so 7 minus x. We go through derivative, du over dx is -1, so 7 goes to 0. Cross multiply, dx equals negative du. Now we make our substitutions. X squared does not get replaced initially. 7 minus x does get replaced with u. And then dx gets replaced with negative du. But now we see that the x squared still does not cancel out. So we're going to now try the change of variable method, okay, where we look at our initial assignment for u being 7 minus x, and we rewrite it in terms, solve for x is 7 minus u. So if we replace x squared in terms of what we assigned, so if x is 7 minus u, then x squared can be replaced with 7 minus u quantity squared. Okay. We can continue with our problem because we have everything in terms of one variable. Now we just have to get this to split up into individual terms. Okay, so I'm going to distribute negative u to the 1/2. The negatives comes from the -1 in front of the du. Through to 7 minus u quantity squared expanded. So 449 minus 14u plus u squared. I'm going to distribute this through. And remember, when I'm combining or when I'm multiplying bases, I'm going to add exponents. So 1/2 plus 1 is going to be 3/2. So distribute through, and I have each term separated by plus or minus. Now we can go through power rule for each term. Okay. So 1/2 becomes 3/2 divided by 3/2 becomes 5/2 divided by 5/2. 5/2 becomes 7/2 divided by 7/2. And we simply flip all the denominators up, multiply through, and don't forget, replace your u back in terms of x, and then don't forget the plus c. All right, number 6, x times 1 minus 2x squared cubed. This is going to be a definite integral problem. So let's see if we can resort to simply using power rule. We can't, or we could, but it's raised to the third power. If we expand it, it may take a little bit of time. So anything more than the squared, we're going to just go through u-substitution. So our u value is 1 minus 2x squared. Find the derivative. d over dx equals negative 4x. Solve for dx. dx is du over negative 4x. And we make our substitution. X initially does not get replaced. Parentheses gets replaced with u. Dx gets replaced with du over negative 4x. Now we see that the x's conveniently cancel out. We pull the negative 1/4 out, and we have integral of u cubed. Okay. Because we're using u-substitution for a definite integral problem, we have to convert our bounds in terms of u as well. Okay. Right now, these are in terms of x. We want these bounds in terms of u. So we look at our assignment here, and we convert. So if x is equal to 1, then we simply plug 1 in for the x here. So 1 minus 2 times 1 squared is negative 1. Our upper bound initially is 2. We plug 2 in for x, and we get 1 minus 8, which is negative 7. So our new lower bound is negative 1. Our new upper bound is now negative 7. Okay. Now when we evaluate, we're going to plug the upper bound in for u first. Upper bound. So negative 1/16 times negative 7 to the 4th minus, always include this minus as part of the first theorem of calculus. Okay, whenever we're evaluating a definite integral. Now we plug in the lower bound. Negative 1 goes in for u. So negative 1/16 times 1 to the 4th. I just went ahead and I just multiplied the 4 together to give me 16. Okay, so we get negative 2401, 2401 divided by 16 plus 1 over 16. The two negatives cancel out, and we're going to get negative 2400 over 16, which reduces to be negative 150.